All right, welcome to the Explainer. Today, we're diving into a force that's completely invisible, but it's so powerful it's responsible for, well, pretty much everything. From a massive bolt of lightning to that tiny spark you feel when you touch a doorknob, this is the force that literally holds our world together. Let's get into it. You know exactly what I'm talking about, right? You reach for a metal doorknob and zap! You get that little jolt, that tiny spark. It's like a mini jump scare from the universe. But have you ever actually stopped to think, what in the world is going on there? Well, it turns out the culprit has a name. It's this fundamental property of matter called electric charge. It's the mastermind behind that little shock, and it is happening all around us, all the time, completely unseen.
So, if we're going to solve this everyday mystery, we've got to start at the beginning. We need to uncover the basics. What exactly is this thing we call charge? Okay, so here's the official textbook definition. Electric charge is just a basic property of stuff, kind of like mass or volume, but its special job is to create an invisible force. It's what lets things push and pull on each other from a distance without ever actually touching. Now, here's what's so cool about this. Nature, in all its complexity, decided to keep this part incredibly simple. There are only just two, flavors of electric charge. And by convention, we just call them positive and negative. That's the whole menu. And these two types of charge, they follow one simple, unbreakable rule that pretty much runs the show. If charges are alike, so a positive next to a positive, or a negative next to a negative, they will always push each other away. They repel. But if they're different, a positive and a negative, they will always pull toward each other. They attract. So yeah, opposites attract isn't just relationship advice. It's a fundamental law of the universe. So we've got two types of charge, and one simple rule for how they dance. But this simple foundation builds up to three core properties that define how charge behaves no matter what. And here they are: additivity, conservation, and quantization. You can think of these as the basic operating system for all electric charge. So let's break down what each one really means. First up, additivity. And honestly, this one is pretty much what it sounds like. If you want to know the total charge on something, you just add up all the little positive and negative charges inside it. The only trick is that you have to pay attention to the signs. So if you have a +5 charge and a -3 charge, your total is +2. Simple as that. Next up, conservation. Now this is a huge deal in physics. It means that in any closed system, you can't just create charge out of thin air, and you can't make it disappear. All you can do is move it from one place to another. You know, when you rub a glass rod with a piece of silk, you're not making new charge, you're just shuffling electrons from the rod to the silk. It's like a perfect cosmic accounting system where not a single cent is ever lost. And finally, the third rule is quantization. And this one might be the weirdest of them all. It means that charge doesn't come in a smooth, continuous flow like water from a tap. Nope, it comes in tiny individual packets. You can have 1 packet or 2 packets or a billion packets, but you can never, ever have half a packet. In other words, charge is digital, not analog. It's one of the first clues we ever got about how weird the quantum world really is. And this is the size of that fundamental packet, the smallest possible piece of charge that can exist. Just look at that number. That's a decimal point followed by 18 zeros and then a 1/6. It is an unbelievably tiny amount. I mean, the amount of charge that flows through a standard light bulb in just 1 second contains over 6 quintillion of these things. It's mind-boggling. Okay, so we know that charge comes in packets, it can't be created or destroyed, and you can add it up. That's all great, but how do we actually calculate the force of all that pushing and pulling? Right? It's one thing to say, hey, these two things push each other apart, but physics is all about numbers. Just how strong is that push? Thankfully, a physicist named Charles Coulomb did the heavy lifting for us. So here it is, his famous law, in all its formal glory. Now, I know that sounds a little dense, maybe a bit like a textbook, but the idea behind it is actually super intuitive. Let's just break it down into plain English. It's really two simple ideas. First, the more charge you have, the more force you get. Makes sense. Second, the more distance between the charges, the less force you get. But here's the critical part. It's inversely proportional to the square of the distance. So if you double the distance, the force doesn't get cut in half. No, it drops all the way down to 1/4 of what it was. This inverse square thing is a huge pattern in physics. So we've got the what, the how, and even the how much. But there's still this one big kind of spooky piece of the puzzle missing. How does this force even work across empty space?
I mean, really think about it for a second. There aren't any tiny ropes connecting two charges. So how does one charge over here know that another charge is way over there? This problem is called action at a distance, and the answer to it is one of the most powerful and beautiful ideas in all of science.
The answer is something called the electric field. Here's the idea. A charge doesn't actually pull on another charge directly. Instead, what it does is it changes the space all around itself. It creates this invisible field of influence. Then, when a second charge enters that field, it feels a force from the field right where it is. The field is like a cosmic middleman.
Okay, but how do you draw something that's invisible? Well, physicists came up with this really clever solution. We use something called electric field lines. They're just imaginary lines, but they give us an amazing visual map of the field's direction and its strength.
And the rule for drawing them couldn't be simpler. By convention, the lines always show which way a positive charge would be pushed. So, for a positive source charge, the lines all point away from it. They radiate outward. And for a negative source, the lines all point toward it. They converge inward.
And these lines have a few simple rules of the road. They always have to start on a positive charge and end on a negative one. They can never, ever cross each other because the force at one point in space can't go in two directions at once. And here's the key. Wherever the lines are bunched up really close together, the field is strong. And wherever they're spread far apart, the field is weak.
And what's so amazing is that when you take these simple rules and apply them to systems with more than one charge, you get these absolutely beautiful, elegant patterns. Like this one here. This is the electric field of a dipole, which is just a fancy name for a positive and a negative charge sitting next to each other. You can literally see the lines flowing out of the positive and curving right into the negative, perfectly mapping that invisible force of attraction. So we started with a simple shock from a doorknob, and we've ended up with these invisible fields that structure the entire universe. It really leaves you with one final big thought. If this is the force that holds atoms together, and atoms make up everything, what part of our world isn't shaped by these simple rules? It's a force that is everywhere, hiding in plain sight.